So our next topic is stars and bars, and the theory is the number of ways to distribute an indistinguishable stones into k piles is this formula, n plus k minus 1, choose k minus 1. Well, how can we derive this? Well, we have our n stones here, and we have k piles. So we think, alright, instead of thinking about putting each stone in a pile, we can think of dividing just this line of n stones into k sections, and that could be our k piles. So like, alright, maybe we can do something like we divide it with lines, like this. And we would have k minus 1 lines to form k different piles, and that could be a combination. So how can we think of something like that? Well, this is where the math gods before us thought of something really clever. If we have n plus k minus 1 objects in a line, we can choose k minus 1 of them to be dividers. So if we choose k minus 1 of them to be dividers, say we choose something like this, we're going to be left with piles and k piles, and this is going to be basically our k buckets or k piles of stones here, the values. So in the end, the number of ways to do it is this: n plus k minus 1 objects, choose k minus 1 to be dividers. Well, although the derivation might be complicated, its applications aren't that complicated. So we start with our first problem. How many positive integer triples ABC satisfy a plus b plus c equals 10? So we might think, alright, what can be our stones in our buckets? The buckets are easy to kind of guess. Well, we can make one A, one of them B, and one of them C. That's not too bad. And if we think, alright, what if we have 10 stones? If we have 10 stones, then if we distribute it among the 3 buckets, we're going to have 3 numbers that sum up to 10. So that's basically 10 stones so far in 3 buckets. So we might be tempted to use this formula directly, but there's a catch. This word positive. Our original formula, we could distribute it something like 505, and that would be counted as valid. But over here, 505 is not valid because 0 is not positive. So here's some kind of like trick. If you want to count positive, you basically subtract n, so you take this and you distribute the n stones or k stones into the buckets, and you're left with some. For our example, we distributed 3 stones, so we're left with 7 and 3. And if we distribute these any way we want, we can get any possible combination that's valid. So we use this formula for n equals 7 and k is 3. We get 9 choose 2 equals 36. Well, that's not too bad. So we go to our next problem. So our next problem is about an elaborate code. And this code features 2 kinds of symbols, left and right arrows. So it's asking how many 3-word code phrases, so words are groups of symbols separated by spaces, use 8 letters. So we think for a moment, alright, so we would think about just using it directly, right? 8 letters, 3 words. But we have a problem here. The problem is indistinguishable. These aren't indistinguishable, there's different types, left and right. So if we have different types like these, it's often helpful to consider that for the end. So we're going to leave the left and right arrows for the end. So if we leave that for the end, now we can pretend we have 8 letters. So we're going to denote letters for L. And we have 3 words. Word 1, word 2, and word 3. But again, like the previous problem, words cannot have 0 letters, otherwise they wouldn't be a word. So like the previous problem, we're going to take some of them and designate them for each bucket. So what that does is make sure all of them have at least 1 letter. We can distribute these however we like. So now we use it for n equals 5, k equals 3. We get 7 choose 2 equals 21. So we have 21 ways to distribute it if all the letters are the same. But now all the letters aren't the same. So we have 21 ways to distribute it. So we're going to have our 21 to the side. And we have 8 characters. So we think, alright, so each character we have 2 possibilities for it, right? We can have left or right. Right? 2 possibilities for this character, 2 for this, 2 for this, and so on. And we have 2 to the 8th different ways of creating a phrase with our characters. So we have, for every way of like 21 ways of distributing the 8 spaces into 3 words, we have 2 to the 8th ways to create our phrase. So we just multiply the 2. So that is just 256 times 21. And after some calculations, we can get 5376 as our answer.